All right, question 12. Which of the following statements about polynomials f and g is or true? Okay, let's have a look at each of them then. So, option 1. If fx is greater or equal to g of x, okay, so g of x is bounded above by f of x for all x greater or equal to 0. Okay, so I'm only considering the positive side. Then the integral between 0 to x ft dt is greater or equal to 0 to x gt dt for all x greater or equal to 0. Good, okay. So what is this statement saying? Okay, this statement is saying that the area under the f curve, all right, is always greater or equal to than the area under the g curve, no matter what interval I take, right? I could go from 0 to 1, 0 to 2, 0 to pi, or whatsoever, right? Okay, so is that true? Well, if you think of this, geometrically, or using a diagram, then it's clear that this must be true, right? Because, okay, let me draw a graph. So f is somewhere flying up here, okay? It doesn't matter what it is. So g is somewhere under here, right? G is below f, right? Okay, so these integrals both start from 0, so I need to start from here. And then I pick some random point. Let's say, okay, 7. Why not? All right? Then it's clear that the area under g, which is the blue part, is much less than the area under f, which is the highlighted part, right? The area under f is this whole chunk, right? So definitely, that statement is more than true. Yep, so 1 is good. Okay, how about 2? If fx is greater or equal to gx for all x greater or equal to 0, then the gradient f prime x is always greater or equal to g prime x for all x greater or equal to 0. Okay, is that true? So let's have a think. So let's try to draw a couple of stuff and see what happens. Okay, so, all right, say, what do we like? Okay, let's use quadratics and linear functions, right? Because that's easier to deal with. So fx greater or equal to gx, right? So let's use a quadratic which actually bounds the line from above, for example, like this. Yeah. Okay, so the quadratic is always above the line, say. All right. Let's make up some random equations for these. So this is y equals to x clearly. What does the quadratic look like? Y equals, say, x squared plus 1 maybe, yeah? Okay, so it has a y-intercept of 1. Cool, okay, so now the fx is greater or equal to gx, right? The quadratic is greater or equal to the linear function. So is the f prime of x always greater or equal to g prime of x? Have a think. So I think not really, right? Because if you look at the y-intercepts, the gradient here is what? 1, right? But then the gradient here is 0. Okay, so the gradient of f is less than the gradient of g, right? So I have found a counterexample to 2, right? So, bad. Okay, how about statement 3? If the gradient of f is always greater or equal to the gradient of g, then fx greater or equal to gx for all x greater or equal to 0. Okay, I think that is even easier than option 2, right? You just consider 2 straight lines, for example, right? You can do something like, let me get rid of this diagram. So you can do something like, okay, fx is greater than or equal to gx, right? So let's take f to be, okay, what do I want? It's 3x minus 5, okay, random function, okay. And you take your g to be 2x plus 6, say, right? Okay, then clearly, the gradient of f is greater than the gradient of g, right? Because 3 is bigger than 2, right? Okay, but then is f of x always greater or equal to g of x? Well, not necessarily, right? Not necessarily, because f is 3x minus 5, so it's something like this, right? Okay, g is 2x plus 6, so it's something like this. G is flatter, right? So it must intercept f at some point, right? Then, okay, fx is greater or equal to gx, that's not true in this region. Yeah, so option 3 is also no good. Cool, okay, so final answer is 1 only, which is option B.